Yeah. Bing. Okay. So in rates, we're going to see graphs like this. So this one tells you that you've got two NO2 and they are falling apart into two NOs and an O2. Does that make sense so far? Like just the reaction that's happening?
Yep.
Okay. So then the next thing that you have to pick out from these guys is why. So let's back up even further. On this side, we've got a concentration axis. So this is this is 0.0025 molar, 0.005 molar, like this. So a lot of times you'll see this written in shorthand, where this is the concentration axis. Like they'll just write brackets. So it could be the concentration of the NO2, like so, or it could be the concentration of the O2, like so, like it's just a concentration axis. And then down below is our time axis. Did it get cut off on your screen? This thing is time in seconds. Okay, so why does the NO2 curve start way up here?
Could you start with your reactants?
Right, yeah, exactly. NO2 is a reactant, and so you start off with a lot of it. The other two start down here at 0 because they're products, and you don't have any products at time equals 0, right? So then what the graph shows is that the NO2 keeps getting lower and lower and lower because of what?
Because the reactants make the product.
Right, yeah. The reactants are falling apart, making the products. So the graphs are, these guys are going up because you're making them, and this guy's going down because it's getting destroyed. Okay. Why? So a couple questions you have to ask. How come the O2 curve is kind of lame down here, where the NO curve, that's pretty exciting, it's shooting up? Like, they're both products. Why do they have different curves?
The coefficient.
The coefficient. So you are making twice as much NO as you are O2. So if we stopped at any time, so let's go like 75 seconds here. If I stopped at that time and just drew like a line going straight up, hopefully these two concentrations are like 1-to-2 ratio. The O2 is half of the NO. Yes, no, is that okay?
Yep.
Okay, now let's clear out that stuff. Let's get rid of it. So the next thing is we only talk in this chapter about what is called an initial rate. Oops, my pen's all laggy. An initial rate. The important word, if I haven't underlined it 75 times, is initial. Okay, so if I've got like a bunch of boys, here's a bunch of boys, la, 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 a bunch of boys, and I've got a bunch of girls, blah, 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 and they're all of marriageable age, and they're all very eager to get married off and start the rest of their lives. So if I like start the clock, everybody's single, everybody wants to get married. Like in the beginning, you're going to see boys and girls start to make couples. Some of them will get married, right? And we can actually calculate like how fast does that happen? Like right now, how many of your friends are getting married?
None.
0.
0. Hey, that's funny. None of my friends are getting married right now either. Like, but when I was 27, 28 years old, I was going to weddings all the time. It was like nonstop weddings. So like the thing is, it's easy to figure out how fast people will get married when you start a problem. Like right now, I would guess that everybody would say, oh, none of my friends are getting married. I've actually had one girl in the last like 10 years whose parents had already arranged for the marriage. And I think technically she was married as a senior, which it's like socially I thought was weird, but like to her parents, that was totally normal. The complicated thing is when you're in your like 40s, most of your friends are married, but they're also starting to get divorced. And so now the data gets weird. You're like, well, I've got all these single friends, but they're singles because they used to be married and now they're divorced. So how do I count them? Like, does that make sense?
Yep.
Yes. Okay, so we have the same issue chemically, that if I have two chemicals, chemical A and chemical B, when I put them together, they're going to make AB. They're going to make some chemical. Bing, bing, blah, 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 la, la, la. They're going to make some new chemical. But the problem is in chemistry, these chemicals, they'll slam into other AB chemicals and they'll break apart back into their original components. Like it's just a natural thing. You're constantly bumping into each other and the chemicals fall apart. So the math gets really hard once you let the chemicals start to react for a while. So what we're going to say is we don't want the hard math. We are going to stop these problems almost instantly. So we're going to say, go ahead and react. Oh, you're done. Okay, like stop. Because if we stop you right away, what percentage of the chemicals have actually married and formed products?
A good percentage.
Oh, mm-mm.
None.
Other way, almost zero. Almost none of the chemicals have formed. So let me show you this another way. So the NO2 in this example is falling apart into these two things, right? But these two things could join back up together and form NO2, right?
Yeah.
The very beginning, if we were to stop this thing right here, how much NO and how much O2 have we formed? Almost zero. So what are the odds that they hit each other and form and go backwards and make the product or make the
Zero. Almost zero. Got it.
So basically if we only look at the very, very, very beginning, we can say, look, these chemicals only do one thing. They're either getting divorced or they're getting married, and that's it. If we wait until longer, you see down here where the graphs are starting to become constant. They're becoming constant because the number of these guys up here that are falling apart are exactly equal to the number that are coming back together.
Okay.
So graph over here is complicated. Graph over here is easy. So we only do initial rates, only. Like, that's it. Now, it's a calculus problem and it's a physics problem because what is the definition of a rate? You have to know the definition of a rate. Come on, physics students.
The change of something over time, like the slope.
Something over time. Oh, wait, come back over here. Change of something over change in time. Exactly. So in chemistry, we are going to be looking at the change in concentration over time. Like chemists are lazy with their language. They just called it a rate, which in a physics class, there are so many rates that like you have to clarify it. But in chem, like this is the rate they're after. So if I gave you a graph of concentration versus time, how do I get the rate from it?
The slope.
The slope. this slope right here, oops, whoop, that slope is my rate. And so if we looked at the slopes, we could also say like, look, this slope and this slope, if we call this slope M, this slope is 1/2 of M. Because if this slope is M, this slope is 1/2 of that. Does that make sense? There might be an easy way to do it. Hold on, let's do it this way. Let's say I call this slope M here. So let's call this slope M. Then this slope over here is
2M.
2M. Because if I'm making one oxygen, I have to make 2 NOs. I have to do it twice as fast. So wait a minute, this slope over here, what's its value in terms of M?
-3M.
Ooh, you're so close. It's definitely negative and it's definitely M, but it's not 3.
2.
Two.
Good work, because it's the same coefficient. So when 2 of these guys disappear, 2 of them form. So they have to have the same slope. Why is it negative slope?
Because it's going down.
Going down, right? So this one's disappearing and these guys are getting formed. So why is the slope, why is the rate getting lower and lower and lower until it drops off to 0? Right?
Because the reaction rates are getting equal.
Yep, exactly. My forward reaction and my backward reaction are becoming equal to each other, which is going to lead us into equilibrium later. Like that's where we're going to start when we say, well, like, wait a minute, like what? So when we talk about equilibrium eventually, we're going to say like, why did it stop here? Why did they level out at this place instead of leveling out somewhere else? And that's a really interesting chemical question. But for now, we just want to look at what are the rates? What are the slopes? Okay. Let's scroll on down here. So here's the next thing. I want to skip that for a second. Let's see here. So rate laws get written in a couple of different ways. There are what are called differential rate laws and there are integrated rate laws, because this is essentially a calculus unit with no calculus in it. If you took this class in college, you would say like, you would need a calculus background. They would like walk you through everything. Here we just say, ooh, there's some calculus happening underneath, but we're going to skip it all and I'm just going to give you the easy version. Now, the easy version of this is that rates, are always written in the same form. Rate, here we go. R equals K times some concentration written to some power. And this thing is called a differential rate law. Okay, so this is one form of the rate law that you're going to see. Now, if there's more than one thing, there could be like, oh, well, what's my other, like maybe there's an A and a B, and maybe there's a C, right? And the idea is like, well, wait a minute, what are these exponents doing? Okay, so let's go back up to my original graph and take a look at it. So do these curves look like anything familiar?
I would assume the answer is yes.
Well, I was hoping you'd go for that, but they're actually pretty complicated curves. This might be like a 1/x curve. It depends. But all the curves look pretty much the same to the naked eye. If you had Lager Pro, you could you could ask Logger Pro, like, what curve is this thing really? But there's no way to just look at it and know. So there could be exponents involved in here, but you can't just tell by looking. So that equation, that differential rate law, you have to find it out by doing experiments. And if we were at school, we would do 2 or 3 experiments where I would have you take data, and then I'd say, stick it in Loggerphone, and we're gonna figure some things out. Since we're not able to do that, you're just gonna have to trust me. So one way that we could do it is that we could get data where I say, well, look, let's say we took chemical A and I gave you a 1 molar solution, find the rate. And you'd say, oh, well, I found the rate. It's 8.4 times 10 to the negative 3. And then I say, okay, do this experiment, same exact experiment again, but this time use different molarity. And you'll notice, hey, wait a minute, the rate also changes. Okay, so if we think about it in terms of getting married, right? If there are billions and billions of young women who are all like single and they're all looking to get married, and there's like one eligible guy, like there's only one eligible single male.
That's a lucky guy.
Yeah, he's very lucky, but you are a girl, you are extremely unlucky. So how often will you get married? Like on average as a girl, it'll be super slow, right? Because the higher the concentration is, the higher the rate will be. So now if we take billions and billions and billions of girls and we take millions and millions and millions of guys and we like stick them near each other, now it'll be like, whoa, everybody's getting married. Because now that the concentration is higher, then it's easier to find somebody to marry. Does that make sense?
Yep.
Okay, so in this case, when I cut the concentration in half, what happened to my rate?
1/4 down.
Ooh, that is the important thing to recognize. So let's do this. So I cut my concentration in half, but my rate is 1/4. So what's going to happen here is if I say rate is equal to some constant, we'll talk about that in a little bit, times my concentration to a power. So my concentration was cut in half, and my rate was cut by 1/4. And I'm going to ignore the constant for a little bit. So what power would I raise a half to get 1/4?
2.
2. So this is actually a second order equation. So these exponents are going to be orders. And in AP Chem, there are only 3 possible orders, a 0, a 1, or a 2. In AP Chem, there are only 3 orders, a 0, a 1, or a 2. In real life, oh, it could be anything. It could be like a 1.25. It could be a 7.6. Like, but in AP Chem, there are only 3, 0, 1, or 2. And so you need to be able to quickly look at things and say like, oh, I just squared that. That's a second order. Like, does that kind of make sense?
Yep.
Okay. So they wrote the rate law down here. Rate equals K times A squared. Just like that. Okay, now one last thing before we run out of time. I hope it's in here. Maybe not. Nope. No, nope, they're not in here. So let's talk about the integrated rate law then. So since this thing is second order, there's another equation that also fits this data. And that equation is that 1 over the concentration at the end equals some constant times time plus 1 over the concentration in the beginning. That's what that little arrow 0 down there means, concentration in the beginning. And you should ask yourself, like, wait a minute, R equals K times A squared. That's the same equation as this equation over here. And the answer is that these things are differential equations. Now, do you learn that in Calc AB or only in BC? Or neither?
I think we went over them in BC.
Got it. So this is like really high level calculus. There's a way to prove that these two equations are related to each other, but that's way outside AP chemistry. So what you'll notice is that on your AP Chem equation sheet, this equation is in there. Okay, that equation is there, and it is your second equation. And that's not an accident. Like, they were so nice to you that the second equation is your second order equation. Your first equation in that equation sheet is going to be your first order equation. And so they're in order according to what order they are. And next time we meet, I'll actually start there, and we'll talk about, like, wait a minute, how are there two equations for the same thing, and how does any of this make any sense? And then how, more importantly, like, how do I remember it? So I posted, there's a worksheet that I posted that's got these 3 graphs. Actually, it's 6 graphs. There's like, I think it's 6 graphs across, and then it lists a whole bunch of equations underneath each one. And we'll start there, and that'll be like how I describe to you, like, look, when you actually solve the problems, they're simple. There are some rules, you need to memorize the rules. That's it.